Chapter 14 highlights the differences between autonomic and somatic nervous systems, but much more so sympathetic and parasympathetic. So the first few slides will be review, which is not uncommon in these nervous system chapters. The second slide of the file reminds us of our map and never split an S, in other words, our hierarchy of the nervous system. And slide 3, obviously, autonomic nervous system and somatic nervous system are both part of the motor. How do I get my pencil to work? There we go. Part of the motor aspect or pathway, right? The effectors of the autonomic nervous system are smooth muscle, cardiac muscle, and glands, and therefore this is a non-willable avenue. Okay, slide 4 is just an introductory slide, therefore useless. Slide 5, these little ovals are actually in our way. So what this looks like on your end, if you're looking at the original slide, right, over here would be somatic, over here would be autonomic. Boy, that's messy. Right? And then the autonomic is further subdivided into sympathetic and parasympathetic. Okay? So let's focus on the differences between autonomic and somatic. They're both motor pathways, but they have different effectors. They have different efferent pathways, and the targets that they feature respond differently to neurotransmitters. And that was slide 6, by the way. On slide 7, just a reminder that the effectors of the somatic nervous system are skeletal muscle, whereas the effectors of the autonomic nervous system are cardiac and smooth muscle as well as glands. Slide 8. These slides look so different through notability. The somatic nervous system features pathways that consist of a single neuron whose cell body is located in the central nervous system. Okay, this cell body is located in the central nervous system and whose axon is heavily myelinated. The effect of the somatic nervous system, or really the effect of this neuron, is always strictly stimulatory, okay? And this little row here is showing us kind of in an almost tabular form that there's a single neuron in this pathway. It's heavily myelinated. Its body is in the central nervous system. We'll, I think, refine that later if I remember correctly. The neurotransmitter that's released at the effector, in other words, the neurotransmitter that's released onto skeletal muscle, the targets, is acetylcholine, stimulatory on skeletal muscle. Okay, whereas in slide 9, wow, they look so different. If we're talking about the autonomic nervous system, well, the autonomic nervous system will feature a chain of 2 neurons in its pathway, a preganglionic and a postganglionic. Yes, we mean presynaptic and postsynaptic, but these 2 neurons synapse in a ganglion because they synapse in the peripheral nervous system, okay? And the preganglionic neuron has a cell body that's located in the central nervous system, whereas the postganglionic neuron, hopefully, obviously, has a cell body that's located in the peripheral nervous system, okay? That preganglionic neuron is lightly myelinated, and it releases acetylcholine. The postganglionic neuron is not myelinated, and it releases either norepinephrine or acetylcholine, specifically on an effector. And the effect may be stimulatory, may be inhibitory. It all depends on what type of receptor the effector is wearing or bearing, okay? So the rest of this slide is, again, that sort of tabular form, okay, where this block represents sympathetic, this block represents parasympathetic, but we'll highlight the differences between the two later. 2 neurons, 1, 2. 2 neurons, 1, 2. However, in this middle image, it's difficult to infer, or at least upon first glancing, that there are 2 neurons, because the illustrator has given us an adrenal gland. We have 2 adrenal glands. They sit on top of our kidneys, and they are strictly innervated by the sympathetic nervous system, which I'll mention again later. And part of the adrenal glands is nervous tissue, and therefore there is a second postganglionic neuron inside the adrenal gland. But the illustrator, in order to show the adrenal gland in its entirety, and therefore in a recognizable form, has to zoom way back, and therefore we can't see that second or postganglionic neuron, but it is inside the medulla, so still a chain of 2, okay? And again, our preganglionic neuron, its cell body is housed in the central nervous system. Our postganglionic neuron is located within a ganglion, or in this sort of weird case of the adrenal gland, is located near the surface of the adrenal gland, okay? Our first or preganglionic neuron is lightly myelinated, and our postganglionic neuron is non-myelinated. And what may be released could be acetylcholine, could be norepinephrine from the postganglionic neuron, where it's always going to be acetylcholine from the preganglionic neuron. Again, the effect may be stimulatory, it may be inhibitory, and again, because we're talking about the autonomic nervous system, the effectors are smooth muscle, cardiac muscle, glands, but not skeletal muscle. Okay, we'll see this again, so no worries. Now, on slide 10 is that sort of tabular form, placing somatic and autonomic into one big table. And this is the way that it's presented in your textbook. Okay? However, you know that, at least for me, I benefit if I can put all the information, or at least maximal information, in one place. So we're going to take this image and we're going to tesserize it. That tesserized version is something that you could only access if you were enrolled in a TESSA section. So, yay! Here on slide 11 is that tesserized version, okay, where we've gotten a little more specific and a little more messy, okay? I've specified that the neuron in the somatic pathway is housed not just in the central nervous system, but specifically in the ventral horn of the spinal cord, okay? I've specified that the preganglionic cell body is housed typically in the lateral horn of the spinal cord. If that cell body is sympathetic, it's housed in typically the brain stem, but we'll be more specific later. If that cell body, that preganglionic cell body, is parasympathetic, I've also specified what type of receptor is worn on the postganglionic neuron, what type of receptor is worn on the effector, okay, throughout the autonomic nervous system. However, these words, nicotinic, muscarinic, adrenergic, they don't make sense to us yet. So we'll certainly learn those, and then you can come back to this, and everything, or much, will be all in the same reliable place, which is nice. Slide number 12. Hopefully you already appreciate that the somatic and autonomic nervous systems can function simultaneously. They're not mutually exclusive. And the example that I usually lean on is if I'm walking along at a good clip with my best, most beloved friend, talking a mile an hour, talking up a storm, and just looking ahead of myself so that I don't trip, because this is my best, most beloved friend, I don't need to turn and look at them every hot second, because I know they're there. They're saying, oh, good. Oh my God, are you serious? Right? They're replying to what I'm saying, okay? Well, imagine that too many seconds have gone by, and I finally realize, wow, my friend hasn't responded. And so I finally turn and look at my friend, and oh no, they've become zombified. Well, my somatic nervous system will respond by sending a motor plan to my skeletal muscles to either run or grab an axe, okay? And in the meantime, simultaneously, my autonomic nervous system will send a motor plan to my sweat glands to increase sweat production, to my heart to increase heart rate, to my heart to increase force of contraction, okay, to my blood vessels, at least some of them, to dilate, vasodilate, okay, to really my amp up, if you will, my sympathetic innervation and kind of downplay my parasympathetic innervation, okay? Now, also, most of the spinal nerves, many of the cranial nerves, house both somatic and autonomic fibers. So there's sort of an anatomical complement to that idea, okay? Anywho, slide 13. The autonomic nervous system is further divided, as you well know, into the sympathetic and parasympathetic pathways. Most of the targets or effectors of the sympathetic nervous system are also innervated by the parasympathetic nervous system. In other words, most targets are dually innervated. Are there some exceptions? Yes. Some of those exceptions, sweat glands, are only innervated by the sympathetic nervous system. Adrenal glands are only innervated by the sympathetic nervous system. The blood vessels that participate in vasoconstriction and vasodilation, and not all blood vessels do, but you'll learn that in more detail in 242, are only innervated by the sympathetic nervous system. And for that matter, erector pili muscles are only innervated by the sympathetic nervous system. But it's these three that are most likely to come back to haunt us, either in this chapter or in 242. Okay? Those are the exceptions, or at least the chief exceptions to dual innervation. Slide 14. There we go. The parasympathetic nervous system, its goal, if you will, is to conserve energy and operate in maintaining the status quo, repair, and nourishment. So let's go ahead and digest that sandwich, all right? And you hopefully already associate the parasympathetic nervous system with relaxation. Blood pressure, despite this slide, it's not as if it's lower than homeostatic balance. It should be at homeostatic balance when someone's relaxing. Same thing with heart rate, same thing with respiratory rate. But yes, low with respect to or in comparison to the sympathetic nervous system, okay? So the parasympathetic nervous system is sending action potentials to help to keep blood pressure relatively low, heart rate relatively low, respiratory rate relatively low, and very, very frequent action potentials, if these are action potentials along an axon, to the digestive system. In other words, increase, promote the digestive activity. Hey mouth, secrete lots of saliva. Hey stomach, secrete lots of gastric juice. Hey small intestine, secrete lots of brush border enzymes, digestive enzymes, so on and so forth, okay? Both the sympathetic and parasympathetic nervous systems innervate the muscles that control the pupil diameter. However, they are separate muscles, so not quite dually innervated. You could say pupils in general are dually innervated, but the muscles that control their diameter are not quite the same. Okay, and the parasympathetic nervous system also innervates the lenses and changes their shape to best accommodate or make them best suited for close vision. Close vision. Okay, the parasympathetic nervous system innervates the muscles that constrict the pupils, narrow down their diameter. Okay, slide 15. Sympathetic nervous system. You might think exercise, excitement, extreme emotion, emergency, embarrassment. They all start with E, so that might be helpful. Frequent action potentials to the heart to increase heart rate, force of contraction, okay? Infrequent action potentials to the digestive system. Don't be active. Don't be particularly active. Digestive system. Frequent action potentials to the sweat glands, which enhances evaporative cooling, of course, and frequent action potentials to the muscles innervated to dilate the pupils. Okay. The effects of vasoconstriction and vasodilation, depending on where the target is for those. In the case of the sympathetic nervous system, will help to direct more blood to skeletal muscles, direct more blood to the heart. Our sympathetic nervous system also serves to dilate our bronchioles, which are some of the most narrow tubes in our lower respiratory tract that actually have enough sort of elasticity to be constricted or dilated, whereas much of the tubing of our lower respiratory tract is sort of locked into shape. It's not constrictable or dilatable, okay? Whereas our bronchioles, at least distally, are, okay? And the sympathetic nervous system also says, hey, liver, thank you so much for storing glucose in the form of glycogen, but can you convert that back into glucose and make it available in the blood? I'm on slide 15. This slide is a little overwhelming at first glance, but it's actually really, really handy because it's driving home that most targets are dually innervated by the parasympathetic and sympathetic nervous systems. So notice that the lenses, the pupils show up on both sides. The salivary glands show up on both sides. The heart shows up on both sides. The stomach shows up on both sides. The lungs show up on both sides. Pancreas, both sides. Liver, gallbladder, both sides. The bladder, both sides. The genitalia, both sides. And some of the chief exceptions are sweat glands, right? Adrenal glands, and not indicated in this image, but we indicated it just a few slides ago. The blood vessels that participate in vasoconstriction and vasodilation, okay? And then also, this image is nice because it drives home that the cell body of the preganglionic neuron, in the case of the parasympathetic system, it's housed either in the brainstem, which is what we noted earlier, or in the sacral region of the spinal cord, okay? Whereas the cell body of the preganglionic neuron, in the case of the sympathetic nervous system, is housed in primarily thoracic, but also possibly upper lumbar, okay? Also, we can recognize that this shorthand means synapse, right? Notice that all of the postganglionic neurons are relatively short on the parasympathetic side, whereas the postganglionic neurons on the sympathetic side, they tend to be much longer. And that's definitely a theme, okay? So let's move on to slide 17, which actually reiterates what we've just established. The parasympathetic nervous system, that preganglionic fiber, it either originates from the brainstem or the sacrum. Its cell body is either in the brainstem or the spinal cord in the sacral region of the spine, okay? Preganglionic fibers are relatively long, or preganglionic axons are relatively long, okay? And therefore they extend from the central nervous system almost all the way to the effector, to the target organ. And they synapse with a postganglionic neuron near or possibly even within target organs, effectors, okay? That means that ganglion is very close to, or possibly even inside, an effector. And that also means that the axon of the postganglionic neuron is relatively short, okay? Slide number 18, another overwhelming image, but it's just driving home for us that preganglionic neuron originates either in brainstem or sacrum. It synapses with a postganglionic neuron in, of course, a ganglion. That's why they're called preganglionic and postganglionic. That is either near or even in a target organ, okay? And this particular image even shows us some of the ganglia names. So, for instance, the ciliary ganglion, the submandibular ganglion, things like that, okay? And let's move to slide 19. The sympathetic neurons. Their cell bodies are either in the thorax, the thoracic region, or the lumbar region, okay? And preganglionic neurons are going to be relatively short. Postganglionic neurons are going to be relatively long, but we'll come back to that, okay? Finally, those rami communicantes that we saw in the previous chapter, as well as that sympathetic trunk, those are going to be relevant. Thank goodness. Okay, and that's what this wormy looking thing in slide 20 represents. This is the sympathetic trunk. So you know that the sympathetic trunk is located alongside the spinal cord. Is very close to the spinal cord, and so that really helps to drive home that yes, preganglionic fibers are quite short for the sympathetic nervous system. Okay, and we'll come back to the rami communicantes aspect soon. One thing I wanted to point out to you are the words celiac and splanchnic. Whenever you see these words, you want to think gut or digestive viscera. Okay? Therefore, if you see the term celiac ganglion, you know that that's a ganglion that houses the synapse between a preganglionic, and a postganglionic neuron in the sympathetic nervous system. Same thing with a splanchnic ganglion, okay? Moving on to slide 21. Here's our spinal cord, our ventral rootlets, our ventral root, our dorsal root ganglion, okay, our very short spinal nerve, really short until it branches, okay, here's our dorsal ramus, and here's our ventral ramus. That's definitely one of our guys that we want to keep our eyes on. It's labeled here as well, okay, and then here is the sympathetic trunk. Right. Featuring at very regular intervals sympathetic trunk ganglia, okay, and then here are the rami communicantes, okay, and now we're finally seeing, one of these is gray matter and one of these is white matter, okay, meaning, or in other words, there's a gray ramus communicans, that's singular, and there's a white ramus communicans, okay? If we think about what white matter means, axons, and what gray matter means, cell bodies and dendrites, we might be able to infer which neuron is housed where. And we might also be able to infer that preganglionic and postganglionic neurons are synapsing here in the sympathetic trunk ganglia, at least for most of the sympathetic system, okay? I'm on slide 22. Now, there are actually 3 different routes that a preganglionic neuron in the sympathetic trunk pathway can take. A preganglionic sympathetic ganglion may synapse with a postganglionic neuron in a sympathetic trunk ganglion at the same level. Or a preganglionic neuron may climb up or climb down the sympathetic trunk and then synapse in a sympathetic trunk ganglion at a different level. preganglionic neuron may pass through a sympathetic trunk ganglion and not synapse in that sympathetic trunk ganglion, and instead synapse in what's called a collateral ganglion. God, how do you spell collateral? I think that's right. Okay, let's look at those. So slide 23. Okay, again, here's our dorsal root ganglion. Here's our dorsal root. Here's our ventral root. Here's our, how do I depict this? Spinal nerve. Okay, here's our dorsal ramus. Here's our ventral ramus. Okay. Here's the cell body, not surprisingly in a lateral horn, okay, of our preganglionic neuron passing through ventral root, which makes sense because it's motor, okay, passing through spinal nerve, okay, and then passing through the white ramus communicans. Why white? Because the preganglionic neuron is lightly myelinated, okay? And in this particular scenario, the synapse between preganglionic and postganglionic is occurring within a sympathetic trunk ganglion at the same level. Here is the cell body of the postganglionic neuron. Okay, here is its axon, okay? Usually when we think of an axon, we think white matter. We don't think gray matter, okay? But in this case, we want to think gray matter because remember, postganglionic neurons are non-myelinated. So when they're clumped together, they're going to be darker in color, okay? Let's look at slide 24. Excuse me. Cell body of preganglionic neuron. Chugga chugga choo choo through the ventral root, through the spinal nerve, through the white ramus communicans, through the sympathetic trunk ganglion at the same level. And in this case, we're ascending, but we could have just as easily descended to a different sympathetic trunk ganglion, okay? And sure enough, here's the cell body of our postganglionic neuron, and its axon runs through the gray ramus communicans because it's non-myelinated. Slide 25. I have no idea why this image is so small. I've tried to make it larger, and it seems to be locked in size. So, pardon this image, okay? Anywho, this is our third possible scenario, okay, which requires a collateral ganglion. Here's the cell body of our preganglionic neuron. Its axon runs through the ventral root, runs through spinal nerve, runs through white ramus communicans, and then rather than synapsing, runs through sympathetic trunk ganglion and extends all the way into some other collateral ganglion, for instance, the celiac or the splanchnic ganglion. Here's the cell body housed within that collateral ganglion of the postganglionic neuron, and it's going to make the rest of the trip for that particular pathway. Okay, so those are the three possibilities. If we go to slide 26, this is an image that isn't from our textbook, but it shows all three possibilities in one image, which is kind of nice to have. Here's the cell body of a preganglionic neuron, okay? We're going to use this one preganglionic neuron to illustrate all three possibilities. Possibility number one. synapse in the same or at the same level within a sympathetic trunk ganglion. Possibility number 2, descend or ascend, okay, and synapse with a postganglionic neuron within a sympathetic trunk ganglion at a different level. Possibility number 3, run on through that sympathetic trunk ganglion and instead synapse with the postganglionic neuron in a collateral ganglion. Okay? Slide 27, we are skipping this quarter. Slide 28, we definitely want to talk about. When a preganglionic neuron is secreting neurotransmitters, it's going to release either acetylcholine. Actually, let me rephrase that. When a neuron in either the sympathetic or parasympathetic pathways secretes a neurotransmitter, it's either going to secrete acetylcholine or norepinephrine. If it's secreting norepinephrine, then it's a postganglionic neuron, or if it's secreting acetylcholine, it's either a preganglionic or a postganglionic neuron. Okay, and all of the autonomic nervous system preganglionic axons secrete acetylcholine. Okay, it's only the parasympathetic postganglionic axons that are secreting acetylcholine. Okay, so parasympathetic post, whereas all pre. Okay, and it's some, in fact most, of the sympathetic postganglionic axons that are secreting norepinephrine. Okay, the one exception is that sympathetic postganglionic fibers that synapse with sweat glands do actually secrete acetylcholine. But because that's the exception rather than the rule, we're going to emphasize that postganglionic adrenergic, neurons are going to secrete norepinephrine. So coming back to now the bold terms on this slide, if a neuron secretes acetylcholine, if a motor neuron secretes acetylcholine, then it's referred to as cholinergic. It sounds like acetylcholine, cholinergic, okay? And if it secretes norepinephrine, then it's referred to as adrenergic. And the root there, good grief, how about legibility? Adrenal. And sure enough, the adrenal gland, or at least part of it, secretes norepinephrine and epinephrine. Okay, it's really that postganglionic neuron that's embedded in part of the adrenal, specifically the adrenal medulla, that secretes epinephrine and norepinephrine. Okay, moving on to slide 29. Neurons that are cholinergic are going to, again, secrete acetylcholine, and acetylcholine will then bind to a receptor on either a postganglionic neuron or an effector, okay? And receptors for acetylcholine are either nicotinic or muscarinic. And the chief reason for the names of these guys is that the drugs, nicotine and Muscarine, think hallucinogenic mushrooms, mimic the effects of acetylcholine. And then whenever a receptor is fitted to norepinephrine, it is either a beta 3, beta 2, beta 1, alpha 2, or alpha 1 receptor. So there are 2 different kinds of receptors for acetylcholine, but 5 different kinds of receptors for norepinephrine. And we could go on and on, excuse me, about the differences. But on slide 30, there's a table that is really going to emphasize what I need you to know, the main gist, okay? And we'll also tie especially nicotinic and muscarinic in with our big tesserized image. Excuse me. Okay, so let's emphasize the adrenergic receptors first. Beta 1, found in the heart, found in the kidneys, okay? And when norepinephrine binds with a beta 1 receptor, heart rate increases, force of contraction increases, and the kidneys release something called renin. And renin, though indirectly, will increase blood pressure, okay? I want you to think beta 1, go heart, go, all right? Beta 2, when norepinephrine binds with a beta 2 receptor. Well, beta 2 receptors are found in the lungs, among other places, okay? Including blood vessels, all right? And beta 2 binding triggers the relaxation of smooth muscle, which, at least where these 2 effectors or targets are concerned, will bring about dilation. So vasodilation and bronchial dilation. Vasodilation and bronchial dilation, okay? When norepinephrine binds beta 3, it's likely in adipose tissue and therefore stimulates adipocytes to generate or produce more lipids, okay? However, we won't emphasize that one. When norepinephrine binds to an alpha 1 receptor, which is found in almost all of the sympathetic target organs, the effect is to trigger smooth muscle contraction. So, for instance, this would bring about vasoconstriction, okay? And then when norepinephrine binds to an alpha 2 receptor, that triggers smooth muscle contraction as well, okay? Oops. And is especially important in the inhibition of insulin secretion. And if you look at the one of the locales of being the pancreas, then that might make sense. Okay? So let's take this information and go to slide 31. Right? Someone has gone through and has specified for you not only which neurotransmitters being secreted by preganglionic neuron, not just which neurotransmitter is being secreted by postganglionic neuron, but also what type of receptor is born on both the postganglionic neuron and the effector. Okay, so notice that if it's a sympathetic pathway, then acetylcholine is what's released by the preganglionic neuron, but we would expect that. Sometimes the receptor is nicotinic. Sometimes, the receptor is always nicotinic. That's nice, okay? And then if we look at the type of receptor that's featured on an effector for synapsing with the postganglionic neuron, okay? That's going to be adrenergic because it's norepinephrine that's released, okay? Now, if we look at the parasympathetic nervous system or pathway, acetylcholine is released by the preganglionic neuron, but we were expecting it. And the type of receptor is nicotinic, all right? Whereas the type of receptor on the effector is going to be muscarinic, even though I agree it's still acetylcholine that's being secreted by the postganglionic neuron. So hopefully that's kind of making sense what I meant originally by, hey, let's put everything in one place. Also, I've specified now which regions of the spine are involved in both parasympathetic and sympathetic pathways. Let's go to slide 32. I cannot emphasize enough how important it is that you sit down and compare sympathetic and parasympathetic nervous systems, either in a tabular form or written out, okay? Maybe a Venn diagram. Let's go to slide 33, and for that matter 34, because they're actually one big table, okay? If we look at 33, we'll see some things that look familiar. We already know that sympathetic and parasympathetic systems target the pupil diameter, okay? We already know that they target the shape of the lenses in the eyes, or the lens per eye, okay? We already know how sweat glands and adrenal medulla are innervated. We also know how erector pili muscles are innervated. We also have talked about how blood vessels are innervated, okay? And we've also emphasized that there are quite a few dually innervated targets or effectors. Okay? The one thing that I want to point out here on slide 34, which is really, really interesting and I think counterintuitive. Erection in both males and females have erectile tissue, is overseen by the parasympathetic system, whereas ejaculation, orgasm, okay, is overseen by the sympathetic system. Kind of counterintuitive. Anywho, know the effect of the parasympathetic and sympathetic pathways on at least six effectors, okay? And that's the end of chapter 14.